Hello and welcome to Chapter 6. We're at an exciting point in the course. By now, we have already taken one exam. We've taken a look at a lot of kind of the basic building parts of business information systems, and now we're ready to press forward to kind of the second portion of the book, which leads us a little bit more into how these data systems are incorporated over big groups, kind of demystify some of the things we talked about earlier. And this week, particularly, we're talking about how information travels, how we communicate, and all those things. A little recap of where we're at in the course. You've had a good amount of time now to start working on those Excel projects. I know in the last lecture, I mistakenly indicated that the projects may be due this week. That's incorrect. If you're watching this the week of September 28th through October 2nd, there's no projects due. The projects are not due until October the 16th, I believe. So glad that we've got that resolved. Sorry about that boo-boo. I hope I did not cause you any undue stress. The next thing is within here pretty soon, the next set of Excel projects and the One Access projects are going to become available to you to start working on, and then those won't be due until near the end of the semester. So I hope you are making some good progress on those. Of course, I'll know how you're doing based on your SAMS grades. I haven't really received a whole lot of communication from you all regarding the SAMS projects. That either means one of two things. The first thing is that everyone is doing an excellent job. They have no questions. The videos are clear. They're moving on with their lives, and that is exactly what I'm hoping for. Or the other thing is that you have not started on those projects, which concerns me. So please make sure that if you have not started on those Excel projects by the time you watch this video, which is, I think we're in week 6 of the course, week 5 or 6 of the course, you need to get those Excel projects. You need to at least get started on them. You only have 3 attempts, and they are not too terribly difficult. Of course, you have the resource of the video to help you get through them, but I don't think there's something you should trifle with. So please do get started and get going on those projects. Last thing, after we wrap up this chapter that talks about communication and delivering information, we're going to have a assignment that deals with this and everything we've talked about in the past couple weeks. So be looking for that assignment next week. I'll go into more detail next week when you get it. And then I guess the last thing is that I hope you have a great fall break after you finish this lecture. And there will be a content quiz, of course, but we'll make that content quiz Monday of the following week after fall break. So you will not have any assignment or work outside of the SAM projects to worry about during your fall break. Okay? All right, with all that covered, let's get going. So let's first talk about our learning outcomes for today. There's a couple things we want to cover, and we want to make sure that we understand these different aspects of information systems. One is data communication, the major components, how processing takes place in these configurations, and then look at some different types of networks. We call these and network topologies. I confuse those two sometimes, but we're going to look at both of those in detail. And then we're going to understand the networking concepts about bandwidth, routers, routing, how wireless and mobile stuff operates, how that phone in your pocket is getting connected to the internet, the importance of wireless security, how we deliver that. We talked at length about security in the past 2 chapters. And then finally, we're going to kind of summarize the convergence between data communications for business applications and personal use. So we've got a lot to cover. I feel like we can cover this chapter in one part, but I am doubtful. So we may take 2 parts, but we'll make sure we get through the information in a way that kind of help demystifies a little bit of what's going on into the book. So let's just jump directly into data communication. And the first thing, we want to kind of define it. And data communication is just the electronic transfer of data from one location to another. And this enables systems to deliver information, and it allows us to do different scenarios of business workplaces. You know, we can have virtual organizations, we can collaborate electronically, but through data communication, we can have things like this course that allows us to connect to one another without ever really being in a physical environment with one another. So that is a basis. Let's talk about what you need to know about as a manager about data communication. And the kind of big takeaway here is that this enhances your ability to make effective decisions, and it allows you to communicate with others in a faster means, which lets you be more efficient and be more productive. Okay. Now, this is not any big mystery. Certainly, we all knew coming into this course that we were going to be doing data communication over a wide span of, physical geography. But this is kind of the language of the industry. And, when we talk about this stuff, we're talking about communicating this information. We call it data communication. And it has certain key effects. One is that it allows online training like this class. It allows us to find information quickly so we can stay up to date. And it helps us become lifelong learners. I think our motto is life, more life, and the spirit makes the master. But it's all about lifelong learning. And that does not always have to come in the form of a course where there's a professor giving lectures and then someone plays the role of the student, but just the same way that you are a student of your social life, you are a student of social media, you are also a student of the world, and data communication really allows us to broaden that out. And ways we can do that are kind of decreasing the boundaries between our work life and our personal life, because we have the ability to do either with our devices. And we can also conference, so we can add a different dimension. It's not just sound, which is something we have had for decades via the telephone, but we can also add video and text, which allows us to have much more rich communication over long distances. So that's the effects. Let's look at some of the just basic concepts in data communication. We'll start with the ones that I think we're most familiar with. Bandwidth. Now, I think everyone has heard of broadband internet, so I'm not going to dive into that. But when that internet gets a little sketchy, that's when we kind of have some attenuation happening. And this is when we lose power as the signal goes from one distance to another distance, or going in between these devices. What you should think about in this instance are those huge power lines that span across the Midwest and kind of scarcely populated areas of the nation or of the world. Well, but from one power line to the next, the signal has to travel. And when we say signal, we're talking something very, very physical. Not signal as in something you can't see, but think of the signal as an electronic pulse. And just like with anything, the further it goes, the less powerful it becomes. So, and when that power begins to just degrade to a point that we can't pick it up anymore, that's when we start experiencing some attenuation. Okay. So, the way we kind of fix this is through a lot of different things. We have devices that get the signal and then amplify it to send it again. But when we lose that signal, that's when we get attenuation. And then broadband is when we just have multiple pieces of data being sent at once. So, for example, bandwidth is how fast you're downloading. These are the commercials you see that say 10.0, 20.0. Attenuation is whether or not that signal is losing power. And then broadband means we can send multiple pieces of data. And of course, on the other end of broadband, if I ask you to guess what the, kind of the opposite of it would be, you would say narrowband, which is narrow being the opposite of broad. Broad means that this is something that is very specific. In this case, when we say band, we're talking about voice grade transmission. And this is stuff that we use for sending audio. Normally, it's a limited amount of information that can be sent through here, but it can be sent at a very high bits per second. So it can be very very high quality. Okay, and quality matters. And then the last thing are protocols. And protocols are the rules that govern this communication. Now, protocols are very important because everything is built on protocols. Think of it this way. Right now, I'm communicating with you. You're receiving my communication. The protocol we're using is English. If I was to just bring together random words from different languages, what I'm communicating to you would be lost because you would not be able to detect if there was an error in what I'm saying. You wouldn't understand when I'm stopping. The concept of periods and commas would go out the window, and you wouldn't be able to really understand it at any important speed because, again, it's gibberish. This is what protocols do for the internet. It allows us to expect data to come in certain lengths at certain speeds and to know when the data is corrupted, and then we can build more complex things on top of it. So I do want you to take away from this that protocols are important. They're not some kind of ambiguous term that we just throw around that is meaningless, but protocols are actually the backbone on which we can build more complex and interesting things. Okay? Some of the components, if we look at it, we have devices that send data, and we have devices that receive them. We have modems, which are modulators, and we'll talk about that in routers. And then we also have a medium over which we communicate, and that is either, kind of a wireless medium or a wired medium. So those are some different components to be aware of. And let's talk about the senders and the receivers. Well, first, the senders and the receivers are either input or output devices. Sometimes we call them thin clients. And what these devices do is they actually kind of live with the network. Okay. And if we think about it, this machine requires the network to work. And since it requires it, we can have different levels of this machinery. And since they're at the end of kind of this communication, we call them the terminal, which is kind of where when something ends, that's where it terminates. That's why we call it a terminal. You may also, the word terminal may be familiar if you've used mass transit before. Trains go in and out of stations and terminals, and we can apply that to information systems. So a smart terminal is a machine that can do some processing of data, but is not a full-featured computer. So what does that mean? Well, your laptop is not a smart terminal because your laptop can operate without the internet, albeit you may not ever want to use it without the internet. It can still operate, it can still do tasks, and can still be very intelligent. A smart terminal needs the internet to really boot up. Everything that it uses is on the network. It pulls it down from the network. It can use it while it's on, but then when the network goes away, so does the functionality of the device. This is different than an intelligent terminal or a personal computer. Now, this is a computer that can do lots of tasks without the support of this network or this main computer somewhere else. So to contrast the two, the smart terminal is a lot like a car in that it can move around, but it still needs all of its processing to be performed by a different entity, and that would be you, the driver. Whereas the intelligent terminal is just you and that. You by yourself. You can walk with or without a car. You can go places, or you can go there quicker with a car. So it's all in where the bulk of the intelligence is. With smart terminals, the intelligence is remote. With an intelligent terminal or personal computer, the intelligence is a part of the computer. And if we expand out a little bit, we can see if we look at intelligent terminals, we have netbook computers. I think most of us should be familiar with that. I'm not going to spend a lot of time there. Or mini computers. Now, a mini computer is your desktop computer. We call it a mini computer because compared to computers of yesteryear, which were huge, mini computers and mainframes are much smaller computers, probably a little bit stronger than your desktop now that I think about it. But these are computers that can really coordinate and synchronize other devices. Okay. And, they receive data that's been processed. They can send it around. But these are kind of the next level up, these intelligent computers. And then the last form we're going to look at, we've looked at kind of medium size, we've looked at large with mainframes and supercomputers. Let's look at very small. And these are smartphones, which you have in your pocket. I'm not going to talk to you about that. And video game consoles, which many of you have probably played, like Xbox, PlayStation 4. And even now, Apple TV is starting to fit the bill for a video game console due to kind of the latest release of that platform. So those are devices. Let's talk about some very specific forms of devices that can send and receive data. Specifically, we'll begin with a modem. Okay. Now, a modem is what we use to connect you to an internet provider, and it's short for modulator. That's the mo, and demodulator. That's the dim. So that's where we're getting modem from. Modulator, demodulator. It's not required for all internet connections, but most internet connections use them. And it comes in different forms. First is dial-up. This is not many people are still using dial-up in big cities. It is happening in rural areas of the nation, but in big cities, most people are not really using dial-up. And dial-up is where we use a POTS signal, which is a plain old telephone signal. So we use the phone line, and you plug it into a modem, and it converts the phone line signal to a computer signal. So actually it demodulates the phone line and then modulates the data back into a phone line signal when it sends it out. Next one up is a DSL, and this is kind of a high-speed phone line service, in a sense, for digital subscriber line. There was a commercial for cable internet they called DSL darn slow line, which I thought was pretty funny. But, it's the next level up from dial-up. And then after that is cable. And cable uses the medium of the cable line, which you would use to connect your television. It uses it for internet connections. And for each of these three, since they use kind of existing technology in a different way, we need something to convert that signal. And we need something to modulate and demodulate the signal as we want to use it. And that's called a modem. Now, when we talk about modems, we can't help but look at communication media, and that is described here. So we have kind of the media that we're using, and then based on whether or not it's a wired or wireless device, we can see how it sends the different information to our devices. I'm not going to dive too deep into this because the book will do a better job really unwrapping this. But if we look at just the wired, so we have a connected media here that's wired, and it splits off to electrical and light. Well, let me ask you the question. When we say light, are we talking about the same light that we would use in a light bulb? Well, actually we are. This light using fiber optics, instead of sending pulses of electricity, now we can just turn a light on and off. Now, if we were to model this in kind of like Bill Nye's The Science Guy, this would be a light switch going on and off that's sending electrical current through the line, but it's also producing bursts of lights from the light bulb. And you can see that if we have the right media and the right kind of connections, we can use all these different ways to send the internet, and we're going to talk a little bit more about each of these as we go on. Okay. So I hope I didn't confuse that too much. On hindsight, I may have made it more confusing than it was without me saying anything, but do review that. Okay. So now there's the communication media. Let's look at how we can kind of process and look at how this stuff is configured. Well, there's three ways that we send data. And in terms of being processed: centralized, decentralized, and distributed. Centralized is exactly what it sounds like. It's done by one computer. So one computer is kind of running this network that we're using. This is what we used in the early days because we didn't have a whole lot of people who knew what was going on, and we didn't have a whole lot of hardware that we could afford. So, the beauty of this, with a centralized system, we have very tight controls. One of the issues, though, is that it is slow. And think of it this way. When you go to Kroger and you're ready to check out, if there's only one cashier available, well, you know what? That cashier has a lot of control on how people check out, but it's very slow and that system's very unresponsive. So when you're checking out, you can wait in line for an hour. Kroger may have been a bad example. Aldi is where this happens a lot. You can go to Aldi and lo and behold, you can be shopping for 15 minutes and checking out for another 15 minutes. But that's a centralized processing. Everything goes through one kind of pipe, if you will, and it gets processed at the end. The opposite of that is a decentralized processing. So, each department, division, each area has its own processing folks. Now the advantage is that it's very responsive, but some of the disadvantages is that it has lack of coordination, and it's expensive because you have more systems. And then finally, everyone's doing the same thing. So we have a duplication of efforts. If we extend the metaphor, now let's say you're at Kroger and there are a lot of cashiers open. Well, now you can check out quicker. But here's the thing. Since before when there was one cashier, if there was an issue that required the manager was probably already there because the manager's attention wasn't divided. So that particular issue would be solved very quickly. In a decentralized process, it's not as coordinated. So, the manager may be off doing something else and has to be pulled in to come and fix the issue I'm having, which, is a disadvantage as opposed to having them there, him or her there already. And then finally, all the cashiers are doing about the same thing, swiping items and charging people. So, we got these two different methodologies. We've got centralized, we've got decentralized. There's got to be a way that we can combine both of these and see if, we can get kind of the advantages of both without having all the disadvantages. And this is what we call a distributed system. And this is where we centralize the control. We still have one brain of the operation, but then we decentralize the operations of the process. So, how does this play out in the example we had before? Instead of having people check out other people, we would do something kind of like the U-scan. We'd have one manager who's kind of with a cluster of U-scans so they can solve problems as they come up. And then the others can kind of by themselves check themselves out. So the operations are decentralized, but the control is still centralized. What are the advantages? Well, we can utilize unused processing power. Now, if we look at this back in information systems, there's a group called SETI, and SETI looks for extraterrestrial life, and they do this by combing through radio systems. Well, SETI has a little app that you can put on your computer, and when your computer goes to sleep, instead of it turning off, it allows SETI to jump in there on your computer and use your computer's processor to do some of the heavy number crunching. And what this does is one of the advantages is it allows you to add computer power to the system. You're not limited by distance, and it's more compatible with growing the program. As SETI's organization grows, well, they can grow this kind of decentralized operation with it with no problem. And the beauty of doing this decentralized approach is that if multiple computers or multiple devices are doing the same thing, if something goes wrong on one, it's easily overcome by just the volume of what's happening. And this allows you to share resources. Now, we're not done with distributed processing because there's even some more advantages we're going to look at. It's more reliable and it's more responsive because everyone kind of is taking the operations upon themselves and they can fix it. But there are some disadvantages, and the disadvantages are significant. They can't be overlooked. You definitely have to provide more security when you are decentralizing where processing's happening. In the example with SETI, SETI has to make sure that when its data is on your local computer, that you cannot disturb the data's accuracy. That well, we talked about in the last two chapters how any good security system is going to make sure that the data is accurate and make sure that the data remains what it was before it was processed. And that's a disadvantage with this because you do introduce risk into the system. Something else is that sometimes you can have incompatibility between equipment. And then the final piece, that managing the network is challenging. And this is something to think about. With every time that we increase the scale of something, we are also increasing the scale of the personnel who have to support that system. And with these distributed systems, there still has to be someone there to guarantee that the network actually comes on. There's got to be someone there to fix any issues or any bugs that are discovered. So managing these networks becomes more challenging as the networks grow and become distributed. Okay, let's talk about kind of network architecture. Okay, so we're going to look at kind of a 7-layer architecture for defining how network data is transmitted. And we're going to look at the different layers in the architecture. And since I think we'll see a chart of this, so we'll just talk about them briefly here, and then you can look at them in more detail in the book. We've got the application level, the presentation level, and that is definitely not PowerPoint when we're talking about the presentation level. We've got the session level or layer. I'm sorry, I should have been saying layer. The transport layer, the network layer, the data link layer, and the physical layer. And the physical layer is what you're most familiar with. That's plugging the network cable into the back of the computer. Okay. And where do we plug that into? Well, at this physical layer point, we plug it into something called a NIC, which is the network interface card. Now, no one calls them NICs except for people who deal in networks. Most of them just call them network adapters. And this operates on the OSI model of data link layers. So the layers are important. We're not going to get too terribly deep into it right now. But it is something that you need to make sure that you are taking a look at and that you do understand. Okay. Now let's move on to the types of networks, because this is pretty interesting. We're going to spend a little bit of time here on types of networks. Then we're probably going to break and pick the rest of it back up in part 2. Okay. So there are 3 types of networks we're going to look at in this course. We call them a LAN, a WAN, and a MAN. Okay. The first, LAN, is a local area network. That's the LA comes from there, and the N is network. And this is when we connect computers that are in close proximity. The next is a wide area network. And this is a network that spans several cities, states, I guess, or countries, but it's a big network. And then the final one is a metropolitan area network. And I wish that these were in order in how the size increases, or even in alphabetical order. I think it would still be a better order. And the metropolitan area network is just a network for a city or connected kind of municipalities. So to get a top view of those, let's start with a local area network, okay? So a local area network has a couple machines. They're connected to a hub. There may be a server, there may not be a server. And then through this hub, which is our either cable modem or a router, we can then connect to the internet. This is a good example of probably how your home networking system is set up. Okay. So, whomever in your house is the most tech savvy, set up a router, they put a password on it, and then you all connect the members of your network, your human network, connect their computers to this local area network. Okay. And this can be wired or wireless or a mix of the two. I know in my home with my wife and I and our children, we've got maybe 20 different devices, 6 iPads, 7 computers. Some are plugged in, some are not. A bunch of television devices. Some are wireless, some are plugged up. So these are examples of local area networks. If we expand it out a little bit further, we're going to jump right to a metropolitan area network. Okay. And this is where we have different networks some big, some small, connected together, and all of them interact with one another. And we've got WAN. We'll cover WAN here in a second. But this is based a lot on the functionality of these networks. So, this group may be the police. This might be an emergency services group. This might be the political network. And these may just be some free wireless networks that are available through parks. But together, they make a metropolitan area network. And then if we want to go broader, we can do a wide area network. Okay. And a wide area network is a network that is connected of nodes from all over the world. So, the internet is definitely a wide area network. It is probably the widest area network until the fantasies of Star Wars and Star Trek become true. The internet is kind of the biggest, broadest, wide area network that's going to be available to us. And then these different networks can exist in what we call different topologies. So let's take just a quick look back at this. And the topology is kind of how these networks connect to one another. And there are a couple different ways. Now they represent a a physical layout. And this talks about kind of the computers and their cables and how they connect to one another. And we have 5 types. We're going to hit them individually. The first type is a star network. And this is where we have a central computer. And then it is connected to all of the different nodes. Okay. Now, the beauty of this one, some of the advantages, it's easy to modify the network because it's got a central computer. You can add networks easily. And it's pretty good at handling short bursts of traffic. The disadvantages, and this, it's the same disadvantages that we have when we were using the centralized network scheme earlier. If the central host fails, we lose the entire network, right? Because everything's within one center of processing. And it gets more expensive as we have to connect more cables to this one thing. Now, the next one is a ring. And a ring is very similar to decentralized. There's no host. Each computer connects to the next computer. So each computer is connected to 2 other people. Transmission, and this only goes in one direction, which is, kind of an interesting way to think about it. You don't need as much cable because the machines are connected to one another, and diagnosing problems do become more difficult here because if you envision the computers connected in a circle, it's almost a lot like Christmas lights. When one goes out and you lose the network, that portion of the network, you may not know exactly where you lost it. Okay. And it's hard to splice another computer into that network. Now, after that, we have what's called a bus topology. And this is where nodes are connected along a network segment. So the ends of the cables are not connected, unlike in the ring. A ring, each computer is going to connect to another computer until it creates a circle. So it's a closed network. In this bus topology, that's not the case. We can just connect computers down the end of the line. And then at the end, we can just hook up a device that's called a terminator. And that means, hey, it'll catch the rest of the signal. Advantages, it's easy to extend. Wiring is not really an issue with this. And it's good for steady traffic. One of the problems is that it's hard to figure out when something goes wrong here because the signal is continuing on past all the computers. So it's hard to figure out where we've got a failure point. Now we've got 2 other topologies. And then after that, we're going to take a break and then dive into the rest in part 2. Okay. So the next one's hierarchical. I am not good at that word. Hierarchical topology. And this is where computers kind of have a relationship where they're on different levels in the organization of the computers with different strengths. So, the strongest computers at the top, we'll call that the mainframe. The next level down would be front end processors. Then the next level, controllers, multiplexers. And then at the bottom, terminals are where people actually conduct workstations. Okay. To extend those words a little bit, a controller is, a hardware software device that controls data transfer. A multiplexer is another hardware device that allows different nodes to communicate with one another. An advantage of this is that it offers control. It's cheaper than a bus or a ring topology in terms of just maintaining the network. But the problem is that it's difficult to expand. Whoa, went a little crazy there. It's a little difficult to expand just because, each top level controller can only have so many different children before it reaches its limit. And that's going to lead to network congestion because, see, if you think about a hierarchy, one and then two below it, and then four below it, and then below that four, we'd have 16. And if we keep going by powers of two, eventually there's going to be a lot of great, great, great grand nodes at the bottom of the network, and they are all still wanting to communicate with their one mainframe. And that is going to cause congestion. Okay? So that's something to really be aware of here. And then finally, another methodology to overcome some of these disadvantages is called a mesh, which is where every node's connected to every other node, or interconnected. It's very reliable. This is very expensive. If you were to think, if you and five other friends were to stand in a circle and each of you took a rope and you and each friend had a rope between you and them, imagine how, you're each holding 6 ropes. So imagine if we expand the network to 50 friends. Now, each and every one of you is holding 50 pieces of rope. This is expensive, because we're talking about not just ropes, but this is actually data wire. This is high-speed connectivity medium being connected from every node to every other node. And it's difficult to maintain this type of network. Not to mention that each of the nodes need to be, pretty strong computers because they're doing all this processing and connecting to all these other computers on their own. So since we've really distributed, or since we've really decentralized this messed up topology, the disadvantages here can be somewhat great. Okay. At this point, we're going to stop. We've reached about halfway through the chapter. Take a look over this. If there's something that you're still struggling with, I encourage you to go back and do those readings, and we'll catch up in part 2.